Hi everyone, I am Dr. Surjit Singh. Today I will talk about Leetcode problem jump game. This will introduce new concepts like memoization and dynamic programming. Let us begin. We are given an integer array. Our aim is to take jumps from start of the array to end. Each element represents maximum jump length possible from that position. In the first method, we will use a recursive function and perform backtracking. Nums is the given list of length 5 and pos can vary between 0 and 4. When pos is 4, we are at the end of the list, which means we have successfully reached the last index. Getting to the last index is the base condition to come out of recursion, and at this point, we will return true to the calling function. If pos is not 4, we will consider the recursive options from pos onwards. Let us begin with pos equal to 0. Value at pos 0 is 2, which means that the farthest jump from pos 0 can be of two steps, that is either to pos 1 or to pos 2, where 4 and 0 are present respectively. Note, a jump cannot go past the last index, so we use the min function to ensure that. We run a loop for trying all possible next positions where pos is 0, value is 2. So there are two possibilities 1 and 2. So loop will run twice, giving us next pos values as 1 and 2. These next pos values will become pos values in the subsequent recursive calls, so these positions are indented right in the display. Also, the call stack is shown at the bottom. So for each of the two possible values of next pos, we will call this recursive function. If either of them returns true, the if statement becomes true, which means that we have reached the last index, and the same message will need to be relayed back in the call stack. So we return true. Consider the first iteration of the for loop, that is when pos is 0, we add it to the call stack and keep the execution pending. Remembering 1 is the first value in the for loop when pos is 0. So a recursive call is made with pos equal to 1. Pos 1 is not the end of the list, so the first if statement is skipped. Value of nums at pos 1 is 4. So the four possible values after 1 are 2, 3, 4 and 5. But position 5 is out of range of nums, and the min function ensures that the furthest jump pos can be to pos 4, and the loop will run for the next pos values, that is 2, 3 and 4. So the execution of pos 1 is also kept pending in the call stack, and in the next call of the function pos becomes 2, which is also added to the call stack. 2 is not the last index. Value of nums at pos 2 is 0, so no jumps are possible, and the for loop is skipped altogether, and the current path reaches a dead end. So the function returns false and pos2 is popped out of the call stack. Function call with pos equal to 1 becomes active once again, and the for loop for pos equal to 1 has finished its first iteration. In the next iteration of the loop, function is called again with pos equal to 3. 3 goes on the call stack. 3 is not the last index. Value of nums at pos 3 is 1, which means only one jump is allowed from this position, that is to pos equal to 4. So in the next call, pos becomes 4. Wow, this time pos is the last index, which indicates success. So true is returned in this function call, and this message of success is relayed back to all the functions in the call stack. Note that 3, 1, 0 were pending in the call stack. Return true ends the execution of the present call, and true is relayed back. Next, 4 is popped out of the call stack, and the function call with pos equal to 3 becomes active once again. The function within this if statement receives true and relays it back. Then pos equal to 1 becomes active once again and receives the true value, and it returns true to the function call with pos equal to 0, which means that pos equal to 0 becomes active once again and receives true. This explains backtracking. Let us now write the main function which initiates recursion. According to the problem definition, the jumps have to start from the beginning of the list, so the main function calls this recursive function explicitly with pos equal to 0, and it receives the return value sent by the final call in the call stack, which is true in this example as we were able to jump to the last index. This means that jumps from beginning to end are possible. In the previous version of the program, the loop runs from pos plus 1 to the furthest position. If we reverse the execution of the loop, the first iteration will be for the furthest position. This could help in reaching the goal quickly in fewer jumps. Let us discuss the time complexity. Number of ways of going from pos to end is double than going from pos plus 1 to end. So a factor of 2 comes with the addition of every new entry in the list. Hence time complexity is of the order of 2 to power n. The recursion call stack has n entries, so space complexity is of the order of n. We notice that often the same position is visited more than once. We can classify the positions as good or bad and save that in a table. This technique is called memoization. Every time we will first consult the table and evaluate only if it was not already visited. The changes regarding status are performed in the same old program, so I will write the two programs side by side. We define an enumerator status for the three possible positions: unknown, good, and bad. We use a global list called status for memoization, which will store the status of all the n positions. The main function canJump is used to initialize the status. We initialize status as unknown for all the n positions in the list, and then the status of last position is changed to good. Now we will call the recursive function with the starting pos equal to 0. In addition to checking the status of the last pos, we will also check the status of all the positions and return true or false depending upon its status. The for loop runs in the same way and the status of next pos is evaluated. If result of the function is true, the same is returned to the parent function, but before returning it, the status of the next pos is saved as good. However, if all the iterations of the next possible positions fail, then the status of pos is bad. This is saved before returning false. Let us discuss the time complexity. The function has a for loop and its time complexity is n. Also, recursive calls this function n times, so the time complexity becomes n squared. Space complexity now is 2n, which is of the order of n. Non-recursive approach is possible if we use a bottom-up approach. We start from a smaller problem and develop till we reach the target. Dynamic programming is easier in a non-recursive approach. Consider the list 31042. In the bottom-up approach, unknown is not required in the enumeration, so good and bad are the only two options. N is the size of the list. All the positions in status are initialized as bad except the last position, which is initialized as good. We run the loop backwards from second last position and set the status for each position. Note that this requires the knowledge of the status of the positions towards its right. Furthest position from pos 3 is 4, which is the last index. We check all the allowed positions from pos plus 1 onwards. If any one out of them has good status, then pos also has good status. As soon as the status is determined, the loop is terminated. In the present case, pos 4 is good, so pos 3 is also marked as good, as position 4 is reachable from pos 3. In the next iteration, pos is 2. As the value of pos 2 is 0, no jumps are possible, so the inner loop is skipped. Next, pos becomes 1 and the value is 1, 2. So we can jump only one step to pos 2. As pos 2 is bad, pos 1 also remains bad. In the next iteration, pos is 0 and the value at pos 0 is 3. So it can jump 1, 2 or 3 steps. In this inspection, a good status is found in one of the three positions, that is in pos 3. So the status of pos 0 also becomes good. The loop is over and status of every position is known. Jumps are possible between all the positions that have good status. As the starting node is good, jumps from beginning to the last index are possible and we return true as the final output. There is a loop within a loop and the time complexity is of the order of n squared. Space complexity is of the order of n, which is the size of the list status. This is the final program that uses dynamic programming without the need of memoization. Consider this list of 8 elements. We set the last position as our goal. We run a loop backwards from the second last position. We try to find if we can reach the goal from the present position. As value at pos 6 is 0, we cannot jump from here. In the next iteration, value at pos 5 is 1, but the goal is more than one position right. In the next iteration, value at pos 4 is 0, so the loop continues. In the next iteration, value at pos 3 is 4 and goal is 4 positions from here, so the if statement is true this time. So we shift the goal to the current pos. In the next iteration, value is 0, so we continue. In the next iteration, value is 1, but goal cannot be reached by a jump of 1. In the next iteration, pos is 0 and the value is 3. And yes, the goal can be reached by jumping 3 steps. So the goal is shifted once again. Now we come out of the loop. We check if the goal has moved to the start. Yes, it has. So solution is true. There is only one loop over n, so the time complexity is linear. Space complexity is constant because we are not performing memoization. Thank you for your time. I hope you have understood the concept of dynamic programming. Please stay tuned.